Polaris, the North Star, has been a constant guide for travelers and explorers throughout history, but up close, it presents a puzzle that baffles scientists. This star, which seems so steady from Earth, behaves in strange and unpredictable ways when examined with modern instruments. The more we learn about it, the more questions we have. Why does Polaris defy our expectations about how stars should act, and why is it so difficult to measure even its most basic characteristics? It's a star that's easy to spot with the naked eye, yet it remains elusive to our most advanced technology. Let's explore what makes Polaris such a fascinating and confusing object in the night sky. On a clear, dark night, you might look up and find the Big Dipper, part of the constellation Ursa Major. The two stars at the end of its bowl point toward a bright, steady light, Polaris. Because it sits almost directly above Earth's rotational axis, it appears fixed in the sky while other stars seem to circle around it. At the North Pole, Polaris is nearly overhead. As you travel south, it appears lower in the sky until it vanishes below the horizon in the southern hemisphere. But while Polaris has helped humans navigate for centuries, the star itself is far more complex than we ever imagined. From Earth, Polaris looks like a single point of light, but telescopes reveal a more complicated picture. In 1779, William Herschel discovered a second star, Polaris B, orbiting at a distance. Over a century later, in 1899, astronomer William Wallace Campbell noticed shifts in Polaris's motion, hinting at another unseen companion. By 1929, spectroscopic studies confirmed a third star, and in 2006, the Hubble Space Telescope captured the first direct images of this trio. Together, these three stars form a triple star system, bound by gravity. The brightest of the three, Polaris Oa, is the star we recognize as the North Star. It's a yellow supergiant, much larger and more massive than our Sun, about 5 times the mass and 46 times wider. If placed in our solar system, it would stretch more than halfway to Mercury, 8 billion kilometers. The third star, Polaris B, is much farther out, circling the inner pair once every 40,000 years at a staggering distance of 386 billion kilometers. That's about 24 times farther than Voyager 1 has traveled in nearly 5 decades, 3 times the mass of the Sun and hundreds of times dimmer than Polaris Oa. But the triple star setup is just the beginning. Polaris Oa belongs to a special class of stars known as Cepheid variables. These stars pulsate in regular cycles, growing brighter and dimmer over time. In the early 20th century, astronomer Henrietta Leavitt made a crucial discovery while studying Cepheids in the small Magellanic Cloud. She found that the brighter a Cepheid is, the longer its pulsation cycle lasts. This relationship turned Cepheids into standard candles, objects whose true brightness can be determined simply by measuring how long they take to pulse. Once we know how bright they really are, we can calculate their distance based on how dim they appear from Earth. It's like knowing the wattage of a light bulb. The dimmer it looks, the farther away it is. Cepheids became a vital step in what astronomers call the cosmic distance ladder, the set of methods used to measure distances across the universe. Before this breakthrough, scientists could only measure relatively close stars using parallax, the tiny shift in a star's position as seen from different points in Earth's orbit. With Cepheids, they could suddenly measure distances to other galaxies, millions of light years away. These measurements help calibrate other distance markers, like Type Ia supernovae, which in turn help us understand the scale and expansion of the universe. As the closest Cepheid to Earth, Polaris should be an invaluable tool for refining these cosmic measurements. It could help us determine the size of the universe, its age, and even its ultimate fate. But here's where things get tricky. There's ongoing debate about how fast the universe is expanding. Some measurements suggest one rate, while others point to this discrepancy has grown stronger as more data has been collected, suggesting there might be flaws in our current models. Polaris Oa is an unusual Cepheid in several ways. First, its brightness variations have been erratic. From the 1960s through the 1990s, the difference between its brightest and dimmest points shrank significantly before leveling off, and then increasing again after the year 2000, a pattern not seen in any other Cepheid. Second, its pulsation period, which is around 4 days, has been increasing by about 4.5 seconds each year. That's an unusually fast change for a Cepheid, suggesting the star is evolving rapidly. One theory is that Polaris A is entering an unstable phase in its life cycle. All stars go through instability when they leave the main sequence, but not all become Cepheids. The type of pulsating star they become depends on factors like mass, brightness, and pulsation period. Most Cepheids experience three major instability phases. The first is brief, lasting between 10 and 100,000 years, and occurs when the star stops fusing hydrogen in its core and begins to expand. The second phase happens when the star starts burning helium, becoming hotter and bluer. The third occurs when the helium runs out and the star expands again. Nearly all the Cepheids we've studied are in the second or third phase, making their behavior more predictable. Catching a Cepheid in its first instability is rare, and their behavior during this stage is poorly understood. There's no consensus on which phase Polaris is in. Some researchers think it's in the first, while others argue for the third. Just as these ideas gained traction, Polaris did something unexpected. Since 2010, its pulsation period has been getting shorter. No one is sure why, though some speculate it could be due to gravitational interactions with its close companion, Polaris AB, as they pass near each other. Even more fundamental than these changes is a basic question that remains unanswered. How far away is Polaris? You might think modern technology would make this easy, but it's surprisingly difficult. For one, Polaris is hundreds of light years away, making its parallax shift extremely small. Additionally, Polaris is so bright that it can overwhelm detectors, leading to unreliable data. Add in its pulsations and the presence of a companion star, and distance measurements become even more complicated. Estimates range from 323 to 520 light-years, and there's still no agreement among scientists. For example, the Hipparcos mission placed it at 434 light-years, while data from the Gaia spacecraft suggests 447 light-years. Without a precise distance, it's hard to determine other properties like mass, size, and luminosity. The estimates shared earlier are based on Gaia data, but using different inputs would yield different results. To make matters worse, Polaris's estimated age, mass, and pulsation period don't match current stellar evolution models. For instance, Polaris A seems much less massive than expected and significantly younger than its companion, Polaris B. We'll return to that age difference shortly. One explanation could be the limitations of the models themselves. Stars rotate, and rotation affects their structure, evolution, and pulsation. However, modeling rotation is complex, and many researchers leave it out. For a star like Polaris A, this omission could lead to significant errors. Another possibility is that Polaris A has lost mass over time, perhaps through stellar winds or interactions with its companions. Some studies suggest it could be losing 2 septillion kilograms of mass per year. That's a 2 followed by 24 zeros, but so far, there's little evidence to confirm this. Recent observations in 2024 also revealed giant star spots on Polaris A's surface, indicating the presence of a magnetic field that might influence its pulsations. If we're missing key physics in how these stars evolve, it could undermine the reliability of Cepheids as standard candles. And if our understanding of Cepheids is flawed, so is our map of the universe. Now, back to that age discrepancy. If Polaris A and Polaris B are gravitationally bound, they should have formed at the same time and be the same age. But observations suggest otherwise. If Polaris is 447 light-years away, Polaris A appears to be around 50 million years old, while Polaris B seems to be about 2 billion years old. So what's going on? One theory is that Polaris B isn't actually a companion, though evidence strongly suggests it is. Another, more intriguing idea involves blue stragglers, stars that appear younger than their neighbors. These are thought to form when two stars collide or merge, creating a star that looks rejuvenated. It's possible that Polaris A was formed or altered by such a merger. While this is still speculative, it highlights how the Polaris system challenges our understanding of star formation and evolution. For now, the age gap remains one of its biggest mysteries. Polaris won't always be our North Star. Earth's axis slowly wobbles like a spinning top, causing the celestial pole to drift in a circle over thousands of years. About 14,000 years ago, the pole pointed toward Vega, and it will do so again in roughly 12,000 years. For ages, Polaris has guided explorers across land and sea. Today, it guides scientists, pushing us to question what we know about stars, the cosmos, and the limits of our own knowledge. With the next release of Gaia data expected in 2026, we may finally gain clearer insights into this perplexing star. If you enjoyed learning about Polaris, consider subscribing to the channel for more fascinating explorations of the universe. Don't forget to like this video and share it with others who love astronomy. Your support helps bring more content like this to life.